Relativity. Einstein overthrew many assumptions underlying earlier physical theories, redefining in the process the fundamental concepts of space, time, matter, energy, and gravity. Along with quantum mechanics, relativity is central to modern physics. In particular, relativity provides the basis for understanding cosmic processes and the geometry of the universe itself. Special relativity is limited to objects that are moving with respect to inertial frames of reference, i.e., in a state of uniform motion with respect to one another, such that an observer cannot, by purely mechanical experiments, distinguish one from the other. Beginning with the behavior of light and all other electromagnetic radiation, the theory of special relativity draws conclusions that are contrary to everyday experience, but fully confirmed by experiments. Special relativity revealed that the speed of light is a limit that can be approached, but not reached by any material object. It is the origin of the most famous equation in science, E is equal to mc squared. General relativity is concerned with gravity, one of the fundamental forces in the universe. Gravity defines microscopic behavior, and so general relativity describes large-scale physical phenomena such as planetary dynamics, the birth and death of stars, black holes, and the evolution of the universe. One of the most famous equations in physics comes from special relativity. The equation E is equal to mc squared, where E represents the energy, m represents mass, and c is the speed of light, which is a constant equal to approximately 300 million meters per second. It shows that energy and mass are interchangeable. They are different forms of the same thing. This equation is one of the demonstrations for why an atomic bomb is so powerful, once its mass is converted to an explosion. The equation also shows that mass increases with speed, which effectively puts a speed limit on how fast things can move in the universe. Simply put, the speed of light is the fastest velocity at which an object can travel in a vacuum. As an object moves, its mass also increases. Near the speed of light, the mass is so high that it reaches infinity and would require infinite energy to move it, thus capping how fast an object can move. Light moves at its speed because photons, the quantum particles that make up light, have a mass of zero. A strange conclusion of Einstein's work comes from the realization that time moves relative to the observer. An object in motion experiences time dilation, meaning that time moves more slowly when one is moving than when one is standing still. Therefore, a person moving ages more slowly than a person at rest. So, when astronaut Scott Kelly spent nearly a year aboard the International Space Station in 2015 to 2016, his twin astronaut brother Mark Kelly aged a little faster than Scott. This becomes extremely apparent at speeds approaching the speed of light. Imagine a 15-year-old traveling at 99.5% the speed of light for 5 years from the astronaut's perspective. When the 15-year-old gets back to Earth, he would be only 20 years old. His classmates, however, would be 65 years old. While this time dilation sounds very theoretical, it does have practical applications as well. A global positioning satellite receiver, also known as a GPS receiver, attempts to find signals from at least 3 satellites to coordinate your position. The GPS satellites send out timed radio signals that the receiver listens to, triangulating its position based on the travel time of the signals. The challenge is, the atomic clocks on the GPS are moving and would therefore run faster than the atomic clocks on Earth, creating timing issues. So, engineers need to make the clocks on a GPS tick slower. The clocks in space tick faster because the GPS satellites are above Earth and experience weaker gravity. So even though the GPS satellites are moving and experience a 7 microsecond slowing every day because of their movement, The result of the weaker gravity causes the clocks to tick about 45 microseconds faster than a ground-based clock. Adding the two together results in the GPS satellite clock ticking faster than a ground-based clock by about 38 microseconds daily. General relativity. Two objects exert a force of attraction on one another, known as gravity. Sir Isaac Newton quantified the gravity between two objects when he formulated his three laws of motion. The force tugging between two bodies depends on how massive each one is and how far apart the two lie. Even as the center of the earth is pulling you toward it, keeping you firmly lodged on the ground, your center of mass is pulling back at the earth. But the more massive body barely feels the tug from you, while with your much smaller mass, you find yourself firmly rooted thanks to that same force. Yet Newton's laws assume that gravity is an innate force of an object that can act over a distance. Albert Einstein, in his theory of special relativity, determined that the laws of physics are the same for all non-accelerating observers, and he showed that the speed of light within a vacuum is the same no matter the speed at which an observer travels. As a result, he found that space and time were interwoven. As a result, he found that space and time were interwoven into a single continuum known as spacetime. Events that occur at the same time for one observer could occur at different times for another. As he worked out the equations for his general theory of relativity, Einstein realized that massive objects caused a distortion in spacetime. Imagine setting a large body in the center of a trampoline. The body would press down into the fabric, causing it to dimple. A marble rolled around the edge would spiral inward toward the body, pulled in much the same way that the gravity of a planet pulls at rocks in space. And these are the citations. Thank you.